Oxidation and reduction reactions are going to involve transferring an electron between two reactants. Now that means that one's got to give up the electron while the other one's going to receive or flat out steal it. And that means one of them is going to be holding it weakly while the other one is grabbing it strongly, or at least more strongly. Now, we can assign oxidation numbers for covalent bonds as well, even though we've usually thought of this sort of a process as happening for ionic substances. And yeah, that's when we definitely brought it up originally, the idea that we could have an electron stolen from one place to another. But we also have the same kind of concept happening when we talk about sharing and uneven sharing. And so this whole phenomenon is going to be similar to what we were talking about when we discussed electronegativity. Now, suppose we look at this example. For H2 and Cl2, these are both going to be elemental forms. Anything that's an elemental form is going to be an oxidation number of 0. And the reason is that there's going to be no change in how it's holding its electrons normally and now. In other words, hydrogen by itself. Hydrogen brought one electron. When we make the molecule, if we stop and look at it, it's going to be totally evenly shared because these both have equally good holds on the electron, meaning that each one ends up getting one electron from it. That means they have the same number as they started with, so their oxidation number will be 0. For the chlorine molecule, same concept. The chlorine atom has 7 electrons on it, and when we make the chlorine molecule, here we are, there's our 14 electrons, 2, 4, 6, 8, 10, 12, 14. 14 electrons on it. If we freeze frame, we see that one electron's here and one's there because they're evenly tugging on that shared pair. So they end up having the same number before and after. But we know that with HCl, this is going to be very polar if we're thinking of it as being a covalent bond. And if we're aqueous, we know it's going to fall apart into the ions, where it's going to be an H plus and a Cl minus. Either way, we're expecting that the H plus is going to have a +1 charge, or oxidation number, and the chloride is going to have a -1 charge, or oxidation number, whichever one you want to think of it as. Now, that might be getting a little bit confusing for how this is different than formal charge, and we're going to get there very soon. The two ideas are going to be tightly related, but we have to make the connection in a moment. Now, they could also form bonds or ions. Either one, we can still calculate an oxidation or reduction number for it. Now, let's go for the example where we've got a covalent bond. In this case, we've got what we just described over here. We have two completely nonpolar covalent bonds. Then over here we have very polar but covalent bonds. And you can see here that we're expecting that the chlorine is going to have about a -1 charge and the hydrogen was going to have about a +1 charge, and that's exactly what we described a moment ago, right? So we can do this for a covalent bond. But did you notice that when I talked about it a little while ago, it was like we were pretending it was an ion, even though it could be covalent? That is the Rosetta Stone for the whole idea. That's what unlocks it for us. When we've got oxidation numbers that we're talking about, it's going to be like we're talking about formal charges. But instead of pretending that everything is evenly shared, we're going to pretend that we're in the completely ionic case, even when it's covalent, and it's going to be winner take all. Whichever is most electronegative gets all shared electrons. And we'll get to see that in a calculation in a little bit in one of our other videos. Now, if we have ionic substances, the full transfer of electrons is exactly what we expected in the first place, and so this holds up with what we were expecting. We expected magnesium, because in column 2, would end up becoming a +2 ion. We expected that oxygen, being in column 6, would gain 2 electrons to become isoelectronic with the noble gas, become a -2 charge, and become the oxide ion. So all of this is still matching up with what we expect from what we've seen before.